Okay, so have you ever just like watched honey kind of swirl and drip? Like in that thick, gooey way?
Yeah, it's mesmerizing.
It totally is. And it got us thinking. So we're diving into this 2-minute papers video today. It basically breaks down how researchers are like pushing the limits of physics simulations to recreate that honey-like effect in computer graphics.
Right, and the thing is, we've gotten so used to seeing like super realistic water and smoke in movies and games, even lava sometimes. But when it
Mhm.
comes to simulating those fluids interacting with like solid objects,
Oh yeah, then things get kind of
a
complicated.
lot more complicated, yeah.
It's almost like the simulation has to like understand that a spoon dipping into honey isn't just passing through it like it would with water.
Exactly.
Got to cling to the spoon, and the spoon's movement should like make those realistic ripples and swirls and all that.
Yeah, and that's where the whole concept of two-way coupling comes in.
Mm.
I mean, simpler methods, they might show the spoon just kind of sinking through the honey as if there's no resistance at all.
Right, right.
But this new research, it introduces this thing called strong two-way coupling, and that captures the physics way more accurately. I mean, the video even shows like a side-by-side comparison.
How cool.
And the difference is just striking.
So with the strong version, we actually get to see the honey supporting the spoon.
You got it.
And all those movements creating the viscous swirls, that's got to be computationally intense to get that level of detail.
Oh, you're absolutely right. It's a constant back and forth between the detail you want in the simulation and the processing time it takes. To get all those fine details, every little ripple and swirl, you need a very granular simulation.
Oh, I bet.
And that can take days, even with powerful computers.
Wow, days, really? So that's where the real, like, innovation of this paper comes in, right?
Yeah, exactly. They came up with this super clever technique that basically changes how the simulation uses its power.
Interesting.
They call it a volume estimation technique, and it focuses the computational heavy lifting on the exact spot where the fluid and solid object touch.
Ah, I see.
Like, think of it as strategically placing your resources to catch the most important interactions.
So instead of, like, simulating the entire volume of the honey in super high detail,
Right.
they're zeroing in on that contact point between the honey and the spoon.
Exactly.
Smart.
And that approach allows them to get both the accuracy and efficiency. They capture those gooey details,
Mm-hmm.
but the rendering time doesn't take forever.
I mean, this is way more than just pretty pictures, though, right? I'm already seeing a ton of potential applications in different fields.
Oh, yeah, definitely. Like in engineering, you could use it to model how fluids interact with structures like bridges or pipelines.
Yeah.
And in medicine, simulating blood flow or other bodily fluids could be crucial.
That makes sense.
And let's not forget the special effects industry. They rely heavily on these kinds of simulations to make those realistic visuals we see in movies.
So it's a scientific advancement, but it also has this very tangible impact, all these different industries. What's the most exciting application to you?
It's tough to choose just one, really. The possibilities are kind of endless.
Right.
But one area I'm really excited about is personalized medicine. Imagine like simulating how different medications would interact with a patient's body, at a molecular level.
Oh, wow. So we could basically run virtual trials before even giving someone a real treatment.
Exactly. Minimize the risks, maximize the effectiveness. It's incredible. And it goes way beyond just meds, too.
Oh, really?
Yeah, we could simulate surgeries, predict how lifestyle changes might affect someone. We could even model how diseases progress, all with much better accuracy.
It sounds like it could revolutionize healthcare, like a more preventative and personalized approach.
Totally. But we got to remember, with powerful tools comes responsibility. We need to make sure these simulations are developed and used ethically. Think about potential biases, protecting patient privacy, all that.
That's a really important point. Ethics can't be ignored as this tech moves forward.
For sure. Now, switching gears a bit, another cool thing about this research is what it tells us about, like, the natural world.
Oh, interesting. How so?
Well, think about it. Even something as simple as honey and a dipper, it involves a lot of complex physics. And by recreating it virtually, we start to really appreciate just how intricate nature is.
It's like we're reverse engineering nature, uncovering the hidden rules that make everything work.
Exactly. And by understanding those rules, we can do more than just create amazing visuals.
Yeah.
We can potentially solve real-world problems, too.
You mentioned engineering earlier. How could these simulations be used for, like, improving how we design structures?
Oh, absolutely. Imagine you're designing a wind turbine
Hmm.
or an airplane wing.
Okay, yeah.
By simulating the airflow around those structures, engineers can actually optimize their shape to reduce drag and make them more efficient.
So it's not just about aesthetics, it's about function too.
Exactly. And this applies to anything where fluid dynamics is involved. Yeah. Cars, pipelines, you name it.
Wow, so we've got this one powerful tool, and it can be applied to personalized medicine, engineering, even just understanding the natural world better. It's a pretty wide range.
It really is. And it shows how interconnected all these different fields are.
Right.
Physics, computer science, biology, engineering, they all kind of come together in this research.
Yeah, it really shows how powerful it can be when, different fields kind of come together, like breaking down those walls between them and seeing how they can all, like, learn from each other.
Exactly. And for someone like you who loves learning and exploring new ideas, I mean, this kind of research it's really exciting. It just proves that there's always something new to discover, even in the most ordinary parts of our world.
When we started talking about honey swirling in a jar, I never thought we'd end up discussing the future of healthcare and how all these different scientific fields are connected.
Right. That's what's so cool about these deep dives. We start with something familiar, and then suddenly we're down this rabbit hole of, like, fascinating connections. But this paper especially, it just shows how these everyday things can lead to these huge innovations.
It makes you want to look at everything differently, like try to find the complexity in the simple things, the things we take for granted.
Exactly. And that's what I hope you take away from this deep dive. I mean, whether it's the way your coffee swirls or how light shines through the window, there's a whole world of amazing things to discover if we just take a moment to look closer and ask questions.
That's a great point, and a great place to wrap things up, I think. So, to everyone listening, thanks for joining us on this deep dive into fluid simulation. It turned out to be a lot more complex than I thought it would be.
It was my pleasure. And remember, the key to unlocking the secrets of the universe. It's simple. Be curious. Keep exploring. Keep learning. And we'll catch you on the next deep dive.